Hello, folks. Well, welcome back. This time we're going to go through the array data type, and there's a lot to consider here. I want to spend some time looking at the different features that they might support, some of the different implementation issues, and we'll play with a little bit of code in C or C++ just to have a look at how some of this stuff is behaving behind the scenes. So let's see where we can get to. Again, the general idea is that we're talking about an ordered collection of elements, right? Just something where we've got a bunch of elements in a row, we're going to access them by position, and it could be a one-dimensional array, could be a multi-dimensional array, right? Different languages support different layers of this, might only support single dimension, might support two-dimensional, might support an arbitrary number of dimensions. One of the things about this is that typically there'll be some form of regularity to the way the arrays are actually stored in memory. To make this effective, usually you're going to say, well, we're going to have some fixed size chunks of memory all in a row to store the different elements that we want to work with. So whether that's saying everything in the array has to be ints, like in C, or ints, or they've all got to be chars, or they've all got to be floats, or they've all got to be whatevers, where you guarantee they're all going to be the same size, or whether it's a more Lisp-like approach where you say, well, what we'll do is actually store the array elements somewhere off in the heap, and then in the array itself, we'll just have references to those. So all those references are the same size. And what that allows the compiler to do is to say, well, every element in there is the same size. If I want to get at element 23, then I just look at where the array starts. I look at the size of a common element, say it's 8 bytes. So I look 8 times 23 bytes down the row to figure out where in memory that particular element is. So it allows a degree of efficiency when you're accessing things and when you're iterating through the array. One of the big things that'll come up as we work our way through this is the resizing of arrays. Does your language allow you to change the size of a particular array as you're working your way along? So we'll come back and talk about that in a little bit. The syntax that you're going to run across for arrays is often one of the things that we find most recognizable about the language that we're working with. So as you're playing with whatever it might be, Bash or Perl or Python or C or whatever it happens to be, one of the things that we always wind up looking at is, okay, well, what's the syntax for an array? What's the syntax for a multi-dimensional array? And that's usually one of the things that if you're looking at a particular program, that can tell you pretty quickly what kind of a language you're looking at. One of the things that's related to that is, in terms of the syntax, usually there's got to be some way for you to tell when you're looking at an array access as opposed to a function call. So if you see foo, some kind of brackets, and a 3, it needs to be distinct both for the compiler and the programmer, whether you're talking about a function call to foo passing a 3, or whether you're talking about accessing element 3 of an array. So there is usually a distinction there. Lisp is a little unusual in that we're using the round brackets for each, and it all looks like function calls, because really it is all function calls or lists. In terms of the declaration syntax, again, there are some languages where you don't have to declare it in advance. Simply when you start using something as an array, it will implicitly declare it there. But again, for languages where you do have to define your array or declare your array, you're often going to have to specify the size and possibly the type. Again, obviously that's not going to be the case for stat or dynamically typed languages, but certainly for languages like C and Java and whatnot, you're going to have to specify what kind of data elements you're actually storing. We're all used to the idea of a zero-based array now, but I'm sure you all remember how strange it was the first time you used arrays when somebody said the first one isn't in, if you've got a 10-element array, the first one isn't in position 1, it's in position 0. And the last one isn't in position 10, it's in position 9. So that's certainly one of the things that you wind up taking a look at as you're getting used to any new language. Storage, again, we spoke about this a little bit earlier, but it might be on the stack or it might be in the heap. Let's say you declare an array as a local variable somewhere in a function. Then It might be the case for your language that it says, okay, well, we'll put the space for that array in the stack frame for that particular function call. Or again, it might be the case that what we'll do is put the space for that array off in the heap someplace, and the local variable in that stack frame will simply be a reference to wherever that heap space is. And when this function call ends, we'll deallocate that heap space. When it comes to declaring things on the stack, one of the big questions is, when do you figure out how big the array is going to be? So it could be the case that at compile time, the compiler actually goes through and figures out, okay, this array has to be of size 27, or whatever that might be. Or it might be the case that it waits until the function call actually takes place, and once we actually go through and create the array on the stack, that's the point where we figure out how big it's going to be and how much space to allocate. So if you look at C, for instance, the idea, especially in the early days, was that you had to have an array size that could be determined at compile time. So the compiler had to know how big the array was. So for instance, you couldn't pass a parameter to a function and use that parameter as the size of an array. It had to be statically known, had to be known at compile time. Let's see, if we are looking at resizable arrays, again, we're going to keep going back and forth to this one, but for resizable arrays, you pretty much have to put them off in the heap someplace, right? You can't have space in the stack frame and, or at least not easily, somewhere during the course of the run of that particular function, resize the stack frame. Right? It's very difficult to manage. So typically, if you're looking at a language that supports resizable arrays, those are going to be somewhere off in the heap. One of the things that we want to look at is how memory is actually organized for a particular array. So again, we mentioned earlier that usually you've got a bunch of cells that are all stored in a row. They're all of the same size, so it's easy for the compiler to figure out what the offset is to each and every cell somewhere off in that array. That does allow for pretty much effective use of both the memory space and efficient access throughout the run of your program. That gets more interesting when we start talking about multidimensional arrays. If you've got a multidimensional array, then we have to figure out what order we're going to store all of the elements in for all of the different dimensions. So for a one-dimensional array, it kind of makes sense that you'd have the first element, then the second one, then the third one, then the fourth one, etc., etc., etc. But if you've got a whole bunch of rows of data, then do you store all of the first row, followed by all of the second row, followed by all of the third row? Or do you go by columns? Say, okay, well, we'll store everything from the first column, and then everything from the second column, and then everything from the third column. So these tend to get referred to as row major order if we're storing it row by row, or column major order if we're storing it column by column. And of course, if you're ever in a position where you need to figure out where things are by memory addresses, like if you're playing in C or C++ or something like that, and you actually want to know what the offsets are to particular elements of an array, then you need to know which of these configurations it's using. So actually, on that note, let's just take a little bit of an experiment here and see if we can play with some a little bit of the C side of things to have a look at what C actually does. So here we have a C++ program actually that's got a two-dimensional array. Right? We've got 3 rows, 4 columns each. And all we're going to do is go through element by element and print out the address of each of them and just see what happens, right? Just see what order it's actually storing these things in. So we've just got a pair of nested for loops. We'll just go through for each row, for each column, print out the row, the column, and then print out the address of that array element. So if you have a look over here, you can see that we're taking the address of that particular array element. Just to get rid of compiler warnings, we're casting it to a void star because that's what the %p formatting option expects. So some of the joys of typecasting. But yeah, let's give that a try and see how things go here. So I'm just going to make sure that I've actually got this compiled, and let's try running these. So again, what we're seeing here is the row, the column, and the memory address for that particular array element. And we're seeing that it's bumping up the address by 4 each time through. And if you look, we're going through and the address is going up by 4s for each of the first row, each of the elements in the first row. And then we're going through and seeing the addresses continue to bump up by 4s. So what we have here is row major order. All of the first row, followed by all of the second row, followed by all of the third row. So again, you can experiment with this stuff. You know, nice thing about C is being able to look at the memory addresses. You can see how it implements things. All right. So again, just a little bit of an experiment there to see how things actually work. Let's see, one of the other possibilities that you might have talked about in 260, the data structures course, is the idea of a sparse array. If you have a really huge multidimensional array, so you've got thousands or millions of rows and thousands or millions of columns, then obviously you can't store the entire thing in memory. So what's done is, usually you're only using a portion of the elements scattered around this array. So you go through and say, okay, well, what we'll do is we'll only store the cells that we're actually using, and we'll take more of a linked list approach to the implementation, where each cell will have a pointer to the next thing on the same row, and it'll also have another pointer to the next thing in the same column. Or maybe in both directions, a pointer to the thing after it and the thing before it in the same row and in the same column. And so if you're traversing through a row or traversing through a column, you can quickly skip over all of the gaps and you don't need to actually store these things. It's slower access, right? If you're going through, you don't have the kind of constant time access where you can just compute the address and jump to it. You actually have to follow these chains. But if you are dealing with really huge arrays where you simply don't have the storage space to deal with it, it is a possible solution. All right, some of the things that we want to consider when we're looking at the complex data types, things like arrays, is if we're going to start passing these things as parameters or returning them from functions, or if we're copying one array to another, how do we do that? Do we actually copy the entire contents of the array from one place to another? Or do we take the approach of simply passing a reference, a pointer, something that says, okay, well, the data's here, when you want to use it, this is where to find it. So you wind up looking at whether or not we're actually passing references, or whether we're passing the entire thing, whether we're doing shallow or deep copies. And of course, that has lots of implications. If you're just passing a reference, or if you're just doing a shallow copy, it's much faster. You're not copying all of those contents. You're not replicating all of that space. But it does open the door to side effects, right? If you change one, you're changing the other. So it gives you the effect of pass by reference in a language like C if you're passing an array to a function. But it does give you that trade-off, right? It's saving you from the need to copy everything into the stack and all of the time that that's going to involve. So it's certainly something that you want to know about with any given language, right? Are we actually passing entire copies, or are we simply replicating, or simply passing a reference to it? A couple of things just in terms of the nuts and bolts when it comes to first creating your array, right? Is an array automatically initialized with any kind of data? Or is it something where, just random data in there, the C-style approach, where who knows what's in a particular position until we explicitly put something there? Do we have any kind of error checking that's inherent to our language that says, okay, I'm going to warn you, you haven't put anything in that cell yet, don't use it yet. We might have support to initialize entire blocks or to assign to entire blocks. Right? If we think of, again, the C or C++ side of things, you can use essentially an assignment statement along the lines of the example we looked at just a few minutes ago. Here, let's bring that up again just for a second. where we can carry out an initialization of all the contents of the array in one statement, but in C or C++, that can only be done at the point where you first declare it. You can't use a statement like this somewhere further down the road. You'll get a compile time error. So one of the things we're always interested in when we're looking at a language is whether or not it is possible to assign values to entire blocks of the array or chunks of the array. Bounds testing is obviously another issue that we're interested in. Is there any automated compiler support that tells us when we're trying to access something that's out of bounds? As you've all discovered in C or C++, I'm sure, you can quite happily trundle off the end of an array someplace and access memory someplace that's completely invalid for what you intended, but there is no bounds testing. Right? As far as the compiler is concerned, it knows where the array starts, and you've told it how far you want to go, and it's just going to figure out where that must be and grab that position in memory. Something that we don't consider too often, but might be a point of interest, is since we've got this idea of a whole bunch of cells all adjacent to one another, if we do have something like overflow or underflow, is there a possibility for destruction of data in one cell to affect its neighbors? The one place where we do kind of see this is where we're, this is more on an adjacent variables side of things, but if we're writing off the end of an array, we do get into this issue of trashing neighboring data. I guess that's not really looking at adjacent cells, but again, you want to be aware of what's happening in memory anytime you're dealing with, well, any kind of data structure like this. All right, so we mentioned array resizing a couple of times as we got into this. So whether or not your language supports array resizing can make a huge difference for the poor old developer. If your language actually supports implicit resizing, then what will happen is anytime you make an out-of-bounds access to an array, it'll go, oh, now I need the array to be that big. So it'll just automatically increase the size of the array to let you use the new spot. Or it might be the case that your language supports resizing, but it has to be explicit. So you actually have to say, okay, now I want this array to be size 1000 instead of size 500. So if it's doing implicit resizing, then it makes it nearly impossible to get meaningful bounds checking, right? Because anytime you use something that's out of bounds, it just goes, oh, that's what you want now, that's what I'll do. With the explicit resizing, then at least you've got the ability to always know that it can tell you when you're accessing something that's out of bounds. Now, we mentioned earlier that the whole idea of resizing can really only be supported if the array is actually stored in the heap, right? If it's stored in the stack, then we have no real way of grabbing new stack space all of a sudden. In terms of trying to actually resize it, if you were making an array smaller, then one of the things the compiler could do is say, okay, well, if you want a new smaller array, then all I'll do is revise my bounds checking idea. So now when you access something, if it's out of the new bounds, then I'll tell you so, but I'm not actually going to do anything with memory. I'll still leave that old space sitting in the heap or sitting on the stack, wherever it might be. But if you ask for bigger space, then all of a sudden you've got this issue of, well, I actually don't have the space necessarily in this one chunk of memory for the new space that you want. Maybe there's stuff on either side of the array in memory right now. What do I do? So the two most common approaches are either to take a linked list kind of approach, where you say, well, we'll have this first chunk of the array at this one location in memory, and I'll have the second chunk somewhere else in memory, and I'll have a pointer that says, okay, well, for the first 1,000 elements, they're here, and here's a pointer to the next 1,000 elements, or the next 500 elements, or the next 60,000 elements. So either you can take this linked list approach, or you can go off and say, well, this space won't work. I better find new space that's big enough for my new version of the array. And so I'll go off and find my space for 60,000 elements somewhere else in memory, move the existing contents to that new location, and then just start using that. Maybe deallocate the space that I'm no longer using and just start using this new space as the location of my array. Now, the big complication there is if we're using a language like C or C++, where we've got pointers or references to that old space, those aren't necessarily getting updated. So if we do some sort of resizing, then we also have to make sure that anything that references the old space gets updated to reference the new space. So we'll come back and talk about some of those issues when we start looking at smart pointers a little later on in the term. All fun and dandy issues to consider. Last thing that I wanted to consider in terms of array operations are some of the fancier things that you might be able to do with an array. So in some languages, you're able to access portions of an array. So let's say we're dealing with a one-dimensional array. Maybe I want to copy elements 1 through 12 as a particular operation. Or I want to copy elements 500 through 507 to positions 0 through 8 of some other array. So this idea of having a subrange of an array and being able to specify that I want to get positions X through Y and support it as a single operation, right? You just have to come up with some kind of a syntax for that. So whether it's an open bracket 3.7 or something like that, and a close bracket to say, okay, there's the range that I want, a syntax that allows you to specify a chunk of the array and do things with that. So that's one possibility. Another possible idea is the notion of a slice. So let's say I've got a two-dimensional array, for instance. What if I wanted to copy just one row of that array in a single operation, or copy just one column of the array and take that in just one operation? Or maybe if I've got a three-dimensional array and I want to take all of the elements that are in row 0, column 0, right, whatever's in that Z dimension, that third dimension, I want all of those elements and grab them in a single operation. So this notion of a slice, again, you have to provide some kind of a syntax to say, well, here's the positions that I want fixed. So for instance, I want column 3, but just give me everything that matches that column. So for a two-dimensional array, that would be everything, all of the row elements from column 3. So all the vertical elements, if you like, in that particular column. So for every row, grab the element in column 3. So this idea of slices could be applied to multidimensional arrays, and you could get a multidimensional slice. Right? You specify a subset of the dimensions, and you just want to grab everything that matches that subset. So it is a fairly interesting idea. Again, different languages will support it to a greater or lesser extent, and it's entirely possible that if you want to do this kind of thing, then you're simply going to have to either use a library function or implement something of your own to accomplish this. But it's certainly a possibility. All right, I think that was everything I wanted to cover in terms of arrays as a data type. Right, you've all had lots of experience with these. As you're going through playing with your C code, I really encourage you to try little experiments along this line, right? Along the line of saying, well, can I figure out where particular rows are, where particular elements are? Can I figure out what the offsets are to specific elements? Right? If we take a look at the memory addresses we've got here, in this particular case, we can simply say, well, it looks like we've got 4 bytes for every element. So if I take the row that I'm on, multiply it by the number of columns, multiply it by the number of bytes, add the number of elements and the size of each of those, I can figure out the offset from the start of the array to any particular element. And that's exactly what the compiler is doing. So, lots of fun to play with. All right, I will leave it there for now, and we will pick up with our next fun and exciting data type next time around.